Okay, so let's go to the next lesson, which is quality attributes. In this lesson, as I said, one of the most important aspects of software architecture is to look at the quality attributes. So, and this is very important. So something that you have to fill in the ARC42 template is what are the main quality attributes, and at the end, software architect has to take into account what are the quality attributes, and those are much more important than the functional requirements from the point of view of software architecture. Quality attributes in a book that I like a lot, and the book changed the name. Instead of quality attributes, they call it architecture characteristics. So sometimes you will find this term, and it's possible that in the future I can even replace by architectural characteristics. And also in some old books, they were called non-functional requirements. The problem of the name of non-functional requirements is that it seems that it's something that doesn't work. It's non-functional. So that's why some people don't like that name very much. Okay. So the types of requirements, there are like three types of requirements. One of them is functional requirements, is a list of the functionality that you want, the how much the system, what has the system to do. So this is if you want to do something in the system, that's a functional requirement. So that's important. How does the system work? How does it react to some runtime stimuli? If you click a button, then it must appear something. That's a functional requirement. And a quality attribute requirement or non-functional requirements are more annotations about the functional requirements. So they qualify. So it's a qualification. It is, for example, imagine that you say in a functional requirement, you can say that if you click in the button to buy a product, then the system will create an order. That could be a functional requirement. A quality attribute, a non-functional requirement, is as an annotation of that. And you can say, okay, if you click in that button to buy a product, then it will create an order in less than 2 milliseconds. Okay, and then you are annotating that requirement, that functional requirement, with some aspect of, in that case, performance. You say, okay, this is less than 2 seconds, so it's on 2 milliseconds, so it must be very fast. So that's when you put those kind of non-functional requirements, for example, usability, security. So you can say if you click to buy an order, the system must be secure or must be very usable. It's very easy to find that button, etc. And there is the other type of requirements are constraints. And I already said that those are design decisions that you don't have to take because they have already been taken by other people. So we are not going to talk too much about constraints, but the main thing about constraints is you have to identify what are those constraints. Okay. Something that I say is that functional requirements and non-functional requirements are usually orthogonal. So you can have a system that has all the functionality, but has nothing, no quality, and that's usually a bad system. Okay, and you could have a system with a lot of quality, but it doesn't do what is required to do, and that's also not very good. Okay? So at the end, it's very important that you move in this point here where you comply with all the functionality and you also comply with all the quality. The corners, I mean, the other places are not very good. Okay. I already said that. So it's quality attributes annotate the functionality. So this is the same example that I put here. They also have a very big influence on the architecture. As I said, quality attributes, you can say, but what is quality? Quality, if you go to Wikipedia, or yes, this is Wikipedia, and you can see what is the definition of quality. Quality is the degree to which a system satisfy the needs of the stakeholders. So taking into account here, we are talking again about the stakeholders. So the degree in which the system satisfies the needs of those stakeholders, that's called the quality attribute. So we are again in the same part as in the previous lesson. You have to know which are the stakeholders, what are the needs of those stakeholders, and then from that identification of stakeholders and expectation of stakeholders, you can create the quality attributes. You can understand what are the quality attributes. And notice in this definition, this is very important, it is a degree. Okay, because this is not Boolean. Quality is not something that you have or you don't have quality. It's usually a degree. You can have more or less quality. Quality is usually defined as fitness for purpose. So in this case, the stakeholders' needs. So, I mean, for example, usually something that makes me very very bad is when I hear someone that says this application has security, or this has scalability. Usually those affirmations those statements are completely wrong, because an application is never 100% secure or 100% scalable. That's impossible. Usually they have better security than other applications or better scalability than other applications, but that's always a degree. Okay, so it's not Boolean. It's something that you can have more security than the previous one, but it's wrong to say that you have security. Okay. Also, you have to conform to requirements, and notice also that the word implied here. There's appear the word implied. Implied means that sometimes those quality attributes are not explicitly stated by the stakeholders. I mean, usually stakeholders are, for example, it is very strange that you go to a customer and they want you to develop some software, and usually they don't tell you, I want the software to be testable. They are not going to ask you for that, because they assume that your software is going to be testable or is going to be maintainable. Okay, what usually they don't go to say that. And usually if you ask, do you want the system to be scalable or to be maintainable, they will always say yes, of course. So this is something, I mean, if you go to the end user and to the customer, if you ask, do you want to have this quality attribute, the answer will always be, of course, yes, we want all of the quality attributes. Okay, so you have to balance that. Okay, and also at the end they have to provide some value. So this is important. It's not to have security because you just want security. It is because you need security for that stakeholder. So as I said here, this is something I'm repeating what I already said. Quality attributes usually are all good. So you want all of them, okay? But the value will depend on the project and the stakeholders. And in some projects, security is very important. Sometimes is not so much important. It's the same in scalability. So you have to understand for what is very important and for whom. Quality attributes usually are not independent, and sometimes they conflict. So sometimes those quality attributes, I mean, it's very difficult to have a very secure system which is also very usable. For example, usability and security usually are confronted, because and this happens, for example, in Solid. In Solid, they put some emphasis on security and to have some kind of security, and that makes the system a bit difficult to have to log in and these kind of things. But that's happening in a lot of things. I mean, it's a lot of things are contradictory, and you have to balance. Okay, and there is always some price to pay for the quality attributes. So you have to understand what is your budget, and you have to balance always, because as I said before, if you ask someone if he wants a quality attribute, he will say that of course. I mean, so that's why I remember in the first years of this course, when we didn't put so much emphasis about the degree and the prioritization of the quality attributes, the students put a list of maybe 20 quality attributes because they say, okay, we want security, scalability, but that's not the exercise. The exercise is to prioritize which are the most important for you. Okay. I said here, there is no single perfect system or architecture. This is also very important. I mean, it's, you have, at the end, the software architect has to find the optimal architecture that he has in that moment, but sometimes what happens is that the same software architect will develop completely different system 1 year after the previous one. So you develop imagine that you have someone asks you to develop one system 1 year, you develop one system, and the next year you are asked to do something similar. You create a completely different system because you have different, I mean, you have learned different things or whatever. Okay. So specifying quality attributes, so two considerations is that quality attributes by themselves are not enough. So it's not enough to have just a list of quality attributes. So if you have, I want to be maintainability, if you don't understand what they mean by maintainability, that's not very useful. So you have to usually specify the quality attributes in some way that they are easy to measure. So that's what we are going to call a quality attributes scenarios. Okay, so a quality attribute scenario is where you say, okay, I have my system and I have some source that provides some stimulus, and I want to understand what is the measure of that stimulus. So that's the way to have a quality attribute scenario. So the stimulus is some event that could be triggered by some person or system, and it will generate a response. So, I mean, probably this is very abstract, so we are going to see it with an example. Let me, for example, here, this is an example. For example, imagine that someone says you, I want the system to be, to have performance. If they don't say anything else, they just, I want the system to have performance, you probably will have a problem to say, okay, performance, what do you mean? And then you have to ask, okay, for performance for you is that if there are 20 concurrent clients, the response time should be less than 1 second under normal operation. Is that performant for you? If he says, okay, that's okay, then you can put that in this way. So in this case, the stimulus, the source is the number of the clients are the source, and the stimulus is that there are 20 concurrent clients using the artifact, the user interface. The environment in this case is normal operation, and the response is less than 1 second in this case. Okay, so this is the response measure. So you can put that in a table and you can say, okay, the source of a stimulus is the clients, the stimulus, etc. Okay, you understand now? So this is usually a quality attribute scenario, and this is something in the ARC42 template. There is a specific section where you can put your scenarios for quality attributes. And my recommendation is that you try to do that. This is a very interesting exercise and you will learn a lot. And of course, there is a question that some people do, is that how we can know about these magic numbers, 20, 1 second, they look like magic numbers. Of course, this is something that you will learn by experience. So my advice is that you at least try to put some numbers. So you can guess some numbers, and later you can refine those numbers. But it is usually very good to put some numbers here so you can measure those quality attributes. Okay. So this is going back to the slides, the components of a quality attribute scenario. As I said, this is the source, the stimulus, the artifact that you are measuring, and the response that you want to measure. Okay. This is another example about availability. Availability, you can say, okay, so, and this is a general of availability. You can say the source could be hardware, the environment, and the stimulus could be there is a fault, there is a mission, a crash, and incorrect timing, incorrect response, and the environment could be normal operation, a startup, shut down when you are repairing the system, etc. So those are the different possibilities for the environment, and the artifact could be the processors, the database, the processes, and the response, how to detect the fault, how to recover from a fault, etc. So those are the different things that you could measure for availability. And the response time could be the time or interval the system must be available, the time in which the system is in a degraded mode, or the time to detect the fault, or repair time, or etc. So these are different measures that you could have. There are a lot of different measures, and I will talk later more about measures, and I have to say that it will depend, and those measures are always changing. So that's why in the course we are not going to go into detail to review all the measures, because probably in your specific project you will have other measures. Okay. The types of quality attribute scenarios are, I found this possibilities. So there are scenarios where you are using the system. So there are usage scenarios. Is, for example, while the system is being used, you should, for example, measure the runtime performance, the memory consumption, the throughput, etc. So those are different things that you could measure while the system is running. There are also scenarios when you change something in the system or some modification. So, for example, if you replace one component by another component, how does that replacement affect the whole system? So those are the special. This is important for maintainability, and there is also scenarios for failure. What happens if there is some part of the system that fails? How does it affect the neighbors? So those are different quality attribute scenarios. Another topic which is interesting and which is important, once you create these tables about quality attributes and scenarios, it's very important usually to prioritize those quality attribute scenarios. So you say, okay, for me it's very important availability, scalability, performance, and you put the different scenarios, and then you have this priority, and usually it is recommended to have these two values, and the values, the meaning of the values is here. How important it is for the success ranked by the customer. So the first value is made by the customer, or the stakeholder. You ask him, okay, for you, this scenario is that when the database doesn't respond, the system should have log the fault and respond with stale data during 3 seconds. Is this very important for you, or is not so much? If he can say, okay, this is of low importance, or this is very high important, and also how difficult it is going to be solved or achieved by the architect. Okay, so if it is going to be very difficult, then you can say, okay, maybe we can wait, and this is not something that we are going to do now, or if the difficulty is very low, then you can say, okay, then we can jump and try to do it in the next iteration, okay, or the next sprint. Identifying quality attributes is also not easy, and there are some techniques to do that, and also there are some lists of quality attributes. Most of the time, the quality attributes are not explicit. So this is important. So this is something that you, as a software architect, have to go and to say, okay, I have to try to dig into the problem and to understand what are the needs and the expectation of the stakeholders to try to obtain some quality attributes. Sometimes they are just verbally mentioned or said during the functional requirements sometimes, and usually they are just implicit. They are just sometimes sometimes someone say, okay, but this should be very fast. Okay, and the performance is important. Okay, so you have to do this kind of educated guesses. This is important. Sometimes there is a technique called quality attribute workshops, where you join or you meet with the stakeholders, and you have a meeting. In a meeting, you try to identify what are those quality attributes, and also there is also some lists of quality attributes. If you go here, maybe I can click. Okay. Let's see if it works. If this link works, there is a list of quality attributes in Wikipedia, and as you can see, you have a lot of quality attributes. I mean, these are 1, 2, 3, 4. I'm not going to count all the quality attributes, but you have a lot of quality attributes, and you have some subsets. And so that I also notice that they are also called non-functional requirements, etc. So you have a lot of quality attributes, and you have to try to understand which are the one. Notice that most of them finish in ility, so accessibility, accountability, adaptability, but some of them no. For example, accuracy, okay, or efficiency. Typical ones are, these are very typical, and in some books about software architecture, they have one section for each of these quality attributes. In the structure of this course, I'm not going to go one by one for each of them quality attributes. Maybe we are going to talk a bit about some tactics for some of them, but this is because this is something which is changing a lot of times. For example, security. Security is something that is not easy because this is a topic which is changing and depends on what kind of system you are developing. Also usability, and also I'm not going to talk a lot about this because you also have this year you have another subject, another course about security. You also have this topic of usability in other courses. So some of them we are not going to talk a lot, but this is important that you look at this. There is this software quality model that comes from this international standards organization, which is called 25010. And here you can see a list of software architecture of quality attributes, and they divide the quality attributes in these two main categories: quality in use. So this is the quality when the system is being run and is being used, and also the quality of the system by itself, so of the product. So this is the functional requirements, the reliability, the secure maintainability, portability. So, and here, if you go, whoops, if you click here, this is something that I hope it is still available. Oh, but it is not available anymore. Okay. So I thought it was going to be available, but it isn't. Okay, I will look at it because this is a list of quality attributes that comes from this international standard organization. A good representation, a good way to represent quality attributes is what is called a quality attribute tree. A quality attribute tree is that you represent the main quality attributes and you put them in this kind of trees. This kind of trees are called a mind map. So this is a mind map, and this is something maybe you saw this representation in other courses or in other places. This is because this comes from psychology, and this is a way that you put in the center of your system the main topic, and then you put branches to different topics in different parts. Okay, so this is a good way to represent the different quality attributes. And also look, for example, in this example I put performance, and then I put latency, and latency here I put the scenario of latency. So they put so this, in this case, the scenario is that you have 20 concurrent users of the system and within 1 second. Okay, this is the previous example. Okay, something which is important about quality, about measurements of quality attributes is that in general it's not very easy to have to provide good measures of quality attributes. Why? Because sometimes the meaning of the quality attributes is very vague, vague. So I mean, it's, for example, if someone says you, I want the system to be deployable or to have scalability. Wow, scalability is a very big topic in itself. Also have a different meaning, because some people could say, okay, but for me, scalability is when this system can have more than 20 users at the same time. But other people, if you go to Google, they can say, okay, but we want 20,000 users at the same time. Okay. Also, there are in some of these quality attributes, they don't have a universal definition. So if you go to, for example, latency, you go to some book and they define latency in one way. You go to another book and they define latency in a different way. So, and then you have to consolidate. That's why, for example, having a glossary in the architecture documentation in ARC42, you have at the end a glossary, is very useful, because then you can say, for me, latency is this, and then you can continue. And also because quality attributes, they usually are composed. So a quality attribute is usually composed by other aspects. So by other features, and so it's difficult to 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 tackle the quality attribute, because, for example, scalability, maybe you have to see which are the different features that you want to measure. But anyway, something that is important is usually that if you measure something, if you are able to measure something, then you know better what you are working with. So if you are able to measure the software system, that's usually better. So one goal, is to have objective measures that you can automatically compute. So you can have some metrics of the system that you can automatically compute, and usually that's a very good goal. Sometimes it's more a goal than something that you can always have, but if you can have this kind of metrics, then you can measure better and you can know better what is the software system that you are developing. Okay, and here you have this link to Wikipedia about what are some software metrics. But again, some of these metrics is just to know that they exist and to use some of those metrics, and you don't have to take them as some kind of religious thing that you have to, okay, this is, I'm going to use this metric because this is very, very always the best thing. Because sometimes if you go, for example, to this Wikipedia article, okay, let's see if it works. Because they explain that better than me. They say that some kinds. Okay, so here you have a list of software metrics, but they said here, I wanted to say this, some software development practitioners point out that simplistic measurements can cause more harm than good. I mean, sometimes if you have a very simplistic metric, that could be difficult. For example, one traditional example here was to measure the productivity of software developers counting the lines of code. And this is very famous. I mean, you go to a company, some companies, some project managers, they want to measure if the developers are working, and they ask, I mean, you can go to GitHub and you can count how many lines of code the developers have been done in one day. Usually that's a very bad measurement, because I mean, it is very easy. You can just copy paste code a lot of times, and you can have people working trying to solve that metric, and so the goal is just to have a lot of lines of code. The more code you add to a system, probably the more problems you will have. And for example, in this book about software engineering at Google, they say that code is a liability, is a responsibilidad, is something that is the more code you add to the code base, the more problems that you will have. So they try to be very, very picky and very selective on which code is added to the code base. So that's also very important. So that's why if you measure productivity of software developers by the number of lines of code, you are doing more harm than good. Okay. Some measures, so here I'm going to put some examples of measures are interesting. I put this one because I think this is, I asked if you had this in other courses. I don't know, probably. Does anyone know about these metrics, about MTBF? Do you know?
I at least have. I don't want to say I have no idea, because maybe I do have it and I don't know that I have it, but I cannot remember it at least.
Okay, so probably you don't know. Okay, okay. So this is a metric which is very popular, especially, for example, for availability. I mean, if you want to, I mean, availability is when you want the system to be running. For example, a typical thing that you go. So this is also interesting. I mean, it's the difference between marketing people and software architects. Marketing people will say that a system has to work 24/7. So it has to work all the time. But if you are a software architect, you know, oh, that's impossible. That's impossible. Even in Google, they don't try to do 24/7 because it's impossible. You always can have some downtime. So a good way to measure availability is to record the mean time between failures. So you can say, okay, how many time is the system working? The uptime, it's called the uptime, and the mean time to repair. So how many time it takes once you have a downtime, how many time it takes to repair and to continue working the system. So if you divide this, then you have a score for availability. And this is an interesting one. And sometimes in some services, for example, in Google or Amazon Web Services, you can even have a contract for the what is called a service level agreement, and they say you, we offer you, for example, availability of 99%. Or sometimes if you pay more money, you can say, oh, no, I want more availability, and they say you will have availability of what is called 4 nines in this case, or 5 nines. 5 nines is 99, 999. Okay, and in these cases, if you have these service level agreements, you can look and say, I mean, you can have this calculus, and you can say, okay, this means that every 90 days, the system will be down 29 hours, or almost 1 day. Maybe this is not very good. So you can say, okay, this is maybe not very good for my project, so I'm not going to take this one. And maybe this one is too much, and maybe if you pay for this, because at the end you can say, okay, but if the downtime by year is only 32 seconds, okay, that's something that I can handle. Notice that, for example, with 4 nines, you can say, okay, this is only almost 1 hour by year, so I can handle all that. Okay, so these numbers are interesting, that you know, and those are some metrics that you can have when, for example, for availability. Okay. This other measure is called cyclomatic complexity. I mean, these are metrics for the software and the code of the software, the structure of the modules, etc. We will talk later more about another metrics for modules, for modularity, but this one, I found it quite interesting because this is also a bit famous, and I asked the other students, and I mean, this is new for this year. They told me that in the degree, there is no other course that talk you about cyclomatic complexity. There is one in 4, but they only just mention it. And this is also very easy to understand. The idea is to have an objective measure of the complexity of your program. Okay, you have a program. Imagine, I mean, this is a simplified program. Imagine this, you have this simplified program and you want to measure if this is very complex or it is very simple. So a way to measure it is that you create what is called a control flow graph. A control flow graph is that you put the, I mean, if it is sequential, this is one block, this is a sequential, but if you have a while loop, notice that is the body of the loop, and then as it is a loop, once you end the body of the loop, you go back to the while. Okay, so you have this loop. And then you have a sequence, which is the next plus plus, and then you have a conditional. The conditional is a branch, so you have two branches, one branch and the other branch, and then you join after the branch. Here, if you look to the code, you have if and the else. Once you finish, you go back, and if the condition is met, you go to the end. So you have this arc that goes to the end. Okay, you understand how to create from a source code, so from a program, you can create this, is called a control flow graph. Okay, I will remove, oops. I will remove, oops. Here, I wanted not to have the annotations here. So now if you want to count the cyclomatic complexity, what you have to do is this formula. The formula is the number of edges in this graph, the minus the number of nodes plus 2. I have to say that the formula is a bit more complex. In general, is 2 multiplied by p, which is the connected components. But in principle, we are going to simplify this for this case. In this case, so you can take into account the number of edges. The number of edges in this graph is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have 10 edges minus the number of nodes. The number of nodes are 1, 2, 3, 4, 5, 6, 7, 8, and 9 nodes. So you have 9 nodes plus 2. So in this case, the cyclomatic complexity is 3. Okay, you understand the formula? I hope yes.
Yes, but
yes.
What I don't really understand is how this can give you like information. I don't understand how this helps you imagine how complex the code is.
Yes, I mean it's not I mean the idea of this is that if you have a lot of loops and a lot of branches, is usually more complex than if, I mean, imagine that you have a program that doesn't have any conditional and any while, so it's just a sequence. If you have a sequence, the formula is going to give you a 1, so it's just 1. You don't have any complex thing. If you have, in the graph, you have, imagine that you start creating a lot of loops, and then inside this loop, you create another loop here, and then here you can go jump here, and you have this branch, and in this branch you have another loop. So once you start creating, I mean, if you create a complex program or a complex algorithm with a lot of loops and whiles and all that, the graph will be much more complex, and probably the number will increase here. I mean, you can take a look and you can see that it's going, for example, I think there is a threshold here, is that if you surpass 10, maybe you have a problem to understand the code.
Yeah.
Okay.
Yeah. So it's complexity in terms of having a simple code to read and to understand.
Yes, well, more than
and to
code,
work with, I mean.
Yes, to work with, exactly. So it's more that the code in itself has a lot of complexity. So you have a lot of loops and conditionals and all that. So usually, if you put, I mean, for example, if you happen to have that in a function, what you can do is to divide that. For example, you can take this part to a separate method, and in that separate method, the cyclomatic complexity maybe is 1, so or 2. And then, so if you have 1 or 2, that's better than having a very big program with a lot of whiles, etc., in the same program. You understand?
Yeah, I get it. Thank you.
Okay, so that's the idea. The idea of, so I again, this is sometimes if you only focus on reducing the cyclomatic complexity, maybe you have another problem. But this is also some metric that in some projects is used to say that at least you should be careful with the code. And I added this cyclomatic complexity this year to the slides because I don't know if you saw it, that if you go to your code rather in this one. No, sorry, it's this is GitHub, Archisoft. This is Viade. So this is from the last year, sorry. Maybe you notice that this is one of you, no? So you have, this is your repos, and maybe you notice that you have this code quality here. If you go to code quality, you have here this 0% and complexity. This measure of complexity of your code is using cyclomatic complexity. So it is looking to the code that you have, and it will, if you have some methods with some complexity, the cyclomatic complexity will increase. Okay, so you have several issues. I mean, those issues, you can take a look later to those issues, but if you have a number here and you don't know how does Codacy know about the complexity of my code, this value is obtained using the cyclomatic complexity and apart from other metrics. Okay, so this is something that is called static analysis methods, which are methods that are analyzing your code without running your code. Okay, so that's the idea of this cyclomatic complexity. Okay, so this is something, that's why I added this to the slide. So later, when you know that Codacy is looking to your code, you know why those numbers, where they come. And for example, the complexity number comes from that. Okay. And there is other measures that you can look in your code. For example, these are called measures of the process in your code. The process is, for example, how to measure the agility or the testability or maintainability of the code. In general, again, these are difficult measures to have objective measures. But some of them are easier than others, and one of them is, for example, the code coverage. And this is something that, again, we added code coverage to your code, and you will later know what is code coverage. And this is the percentage of lines of code that have been run during the testing phase. For example, in radaring, I'm trying to explain something that you will later. I don't know if you already know about continuous integration. In the next lesson, in the next day, we are going to talk about continuous integration. This CI comes from continuous integration, but this code cov, maybe you didn't know what it is. So this is code coverage, and this means that when the system is testing your code, it means how many lines of code has been tested, have been run during testing. In this case, if you click here, for example, this user list during the test have been run that method, but as you can see, there are other methods that have not been run during the test. Okay, that's why you have 39%. So this value is not very good. Usually, a good goal is to have here around 60%. For example, if we go to see some project from last year, oops, well, this is the same one, exactly. So this is also not very good. Those are not very good. Okay, so in principle, this one should be better. Okay. Oh, I know. trying to see if some of this is okay. This one is a bit better. Okay, but also again, we are not. My view here is that you should be pragmatic with these numbers, and you should try to improve those numbers. But it's not a religion. It's not something that you have. This mandatory. Okay, you have to improve them, but that's okay. And also about deployability, you have other numbers like the percentage of successful deploys or how long deployment takes, issues, bugs, etc. And finally, something which is important nowadays is I have seen this in 2 books about software architecture from the last year. Now they are talking more and more about what is called evolutionary architectures. Evolutionary architectures are you have an architecture of your system, you have some metrics about different aspects, for example, the complexity or the code coverage, and then you put all those metrics in a function. That function is called the fitness function. The fitness function is how well is your system working, and the idea is that if you do some change in the architecture, you are trying to improve that fitness function. So it's a mechanism that provides some objective assessment of the integrity of the system combined with quality attributes. So that's the main way of this slide here. The main goal is that you understand that you have to, in some kind of to have some government of the quality attributes along the project. So when you are working with the project, you have to be careful with how the measures of the quality attributes are evolving with the project. And that's all for this set.